Welcome back to the second part of Trig 5.5 notes. We finished up we started the previous problem here. We got to the part where we were solving for k. So now when we look back at the problem, once we know what k is, we can answer the second part, which is finding the population in the year 2010. So I'm trying to find the ending population with the starting population at 25,000. And the k we found as 0.0447, and the time, if year 1990 is 0, from 1990 to 2010 would be 20 years. So these are going to be the numbers we're going to plug into our equation. So plugging this into our equation, we would say y equals 25,000 e raised to the 0.0447 times your time of 20, and we end up getting a y value of 61,122 if I round it to the nearest person for this answer. Alright, so we have a scientist who notes that the bacteria in a count in a petri dish is 50. 2 hours later he notices that the count has increased to 80. So we're going from 50 to 80, so we know that this is growth. And we're going to use this equation then because it's exponential growth. And it says that we start off with 50 and we end with 80. So our initial will be 50, our ending will be 80. And that happened in a matter of 2 hours. So our time is, and they use x up here for time. I guess I'm in the habit of writing a t. So put that as a t. Is 2. So we're trying to find then our growth rate. That's what we don't know. So this is the first thing that we'll do. Plug in 80, plug in 50, plug in a t of 2, so bp times 2. Our goal here is to isolate this e, so we're going to get rid of the 50, so we'll divide by 50. So I'll get 8/5 when I do that. And then e of 2, or e raised to the 2b. Again, to be able to work with this, I would have to apply natural logs to both sides, and that will allow me to write my exponent as a coefficient. So the natural log of 8/5 equals 2b times the natural log of e. Now again, remember we discussed that the natural log of e is the same as 1, so we just have to divide by 2. And when we do that, we're going to get a b value of 0.2350. Again, we'll round that to 4 decimals. Got a positive number, which is good because this was a growth rate problem. We were increasing the number of bacteria. So now the second time that we do that, we can actually answer the second part of the problem. So if this growth rate continues, how much more time will it take for the bacteria to reach 100? So we want the ending population to be 100. So our ending will be 100. We started off with 50. That doesn't change. And we know our growth rate is 0.2350. We want to know the time that it will take to get there. So that's what we're going to find. And we'll deal with this idea here of how much more time once we get our answer over here. So let's go back to our formula. We'll plug in 100 for y. A is going to be 50. E is e. B is 0.2350. And we will solve for time. So isolate the e. We divide by 50. 2 equals e raised to the 0.2350t. To solve this, we would have to apply natural logs to both sides, which will allow us then to write our exponent as a coefficient. And remember, the natural log of e is 1, so we divide by 0.2350, divide by 0.2350, and I end up getting 2.95 if I round that as t, and that would be hours. Now the question though said, how much more time will it take? So really what I wanted to know was, how much time would it take to go from 80 to 100? Is what I wanted to know, but I found it as 50 to 100. So I know that to get from 50 to 80, it took 2 hours. So from 50 to 80 was 2 hours. And if from 50 to 100, it was 2.95 hours, that would mean that from 100, or from 80 to 100, it'd have to be 0.95 hours. Now we probably won't give our unit of time as 0.59 hours. So 0.95, and I know that each hour has 60 minutes in it, 0.95 times 60 would be 57. So we'd probably more than likely give our answer as 57 minutes. You could write it as 0.95 hours, that would be correct also. 57 minutes just makes a little bit more sense. Alright, looking at this next problem, it says a conservation group releases 100 animals of endangered species into a game preserve. The organization believes that the preserve can carry 1,000 animals at its max. And this time they're not giving us the growth rate curve, they're giving us a logistics curve, so they're giving us the formula right here. P equals 1,000 divided by 1 plus 9e to the negative k plus t, where t is measured in years. So it says if the herd size is 134, that would be my ending population, after 2 years, find the population after 5 years. So looking at this formula here, the things that I don't know are P, K, and T. K is my growth rate. We don't really worry about the negative here because it's not in the form we're used to seeing. When it's in this form, that's when K is negative. It means decay. This is going to be growth because we start off with 100 and now after 2 years we have 134. So because we're using a little bit different of an equation, we don't have to worry about using it in this form because they're giving it to us here. So our P, which is our ending population size, so normally that was our Y, but our P is going to be our ending population, would be 134. K is what we're trying to find, and we want to know if the population is 134 after 2 years, that would be, time would be 2. Let's plug that into our problem here. So this is what we'll do first. 134 equals 1,000 over 1 plus 9e to the negative k times 2. Algebraically, to solve this, my problem is I'm trying to solve for a k that's in my denominator. To get that to go out of the denominator, I would have to multiply both sides by 1 plus 9e to the negative 2k. And same thing over here. 1 plus 9e to the negative 2k. So really what that's going to leave me with is 134 times that whole quantity. And over here, these will cancel out and leave me with just 1,000. Now I can start to get this e by itself. Get rid of the 134. So 1 plus 9e to the negative 2k equals, when I divide this out, and I'll change it to a fraction so that I'm not rounding yet, it would be 500 over 67. Keeping in mind that I'm trying to isolate this e, I have to subtract 1 now. So when I subtract 1 from that, I end up getting 9e to the negative 2k equals 433 over 67. Again, keeping it as a fraction. Then I have to get rid of the 9, so I'll divide by 9. I'll write that up here now. I end up with e to the negative 2k equals 433 over 603 now. Now I'm at the point where I can actually apply logs to both sides to be able to solve this. So I'm going to have to apply the natural log to both sides. And the reason I do that is so that I can move the negative 2k as a coefficient. So the natural log of e is 1, so now I divide by my negative 2, and I end up getting my k to be equal to 0.1656. So even though in here it was negative, Again, we got a positive answer, which is good because we know that a positive k means we're growing, and we were growing. We went from 100 to 134. Okay? So now what I want to do is I want to find the population after 5 years. So the second time that I do this, I want to find the population. So I want to know what p is. I know what k is, 0.1656, and t is 5 years. So I'm going to use this information and plug it into there to solve. So let's do that over here. P is equal to 1,000 over 1 plus 9e raised to the negative from here, the fact that k is negative even though it's positive down here, 0.1656 times 5. Now when you do this, let's get an answer for this denominator first. When I go through and I do 1 plus 9e raised to that negative exponent, I end up getting 4.9323000318. And again, I want to keep that whole entire decimal in my calculator. So I would again pause the video, make sure that you can get that correctly entered into your calculator. And then we would find that our answer would be 202.74, so because it's the number of animals, we would say it's about 203 animals after 5 years. Okay, Richter scales, those that measure the intensity of earthquakes, are based upon the log formula R equals the log of I, where R is the Richter scale reading and I is the intensity. So, if we know that in 1906, the earthquake in San Francisco measured 8.6, so our Richter scale reading was 8.6, the intensity is what we're trying to find. And in 1989, the Richter scale reading was 7.7, and we want to know what the intensity is for that earthquake. So, if I use the formula R equals the log of I, we would put in 8. Let me write that down over here first. R equals the log of I. We would put in 8.6, and we would try to solve it for I. Over here, we would put in 7.7 equals the log of I. Now to solve this problem, it's the log equal to a real number on this side, so we have to write it in exponential form. Now remember that the log has an imaginary base of 10. So this would be 10 raised to the 8.6 is the intensity. This one would be in exponential form. 10 raised to the 7.7 is the intensity. So if I plug that into my calculator, 10 raised to the 8.6, I get a pretty big number here. 398,107,170.5 as the intensity. And this intensity would be 50,118. Sorry, 50,118,723.4. That's right, would be the intensity. But really what the problem is asking is it wants me to compare the two intensities. You know, if I look at the Richter scale reading, they're less than 1 unit apart. You know, an 8.6 versus a 7.7. So I may say that these would be pretty comparable earthquakes. But really when I look at the intensity, this is about 50 million. This is more closer to 400 million. I can see pretty clearly that this one is 8 times bigger. So the way that I'm doing that is I'm taking this one, which was 10 raised to the 8.6, and dividing it by 10 raised to the 7.7, and I'm getting it to be approximately 8 times as intense. And so we're really talking about the 1906 earthquake was more intense than the 1989 earthquake by a scale of about 8 times. Now, I've never been in an earthquake, but I know that an 8 times as large intensity of an earthquake is going to be a huge difference in comparison.